for our heap implementation, we are going to use array list. So array list is probably is in Java util, part of your Java collections interface. So this array list is essentially just a dynamically resizable array, right? We're passing in a generic t. So this t could be a string, it could be an integer. It depends on what type of elements that you're trying to store inside this heap. So this priority queue or heap, right, is represented in a flat one-dimensional array list. So there's a couple of global instant variables that we have to keep track of. One is last index, one is max index. So let's just say this is an array list, and your capacity is the max index. Okay, so this is basically the last elements, right? That would be at. So if your capacity is 100, then your max index is 99, right? Because array indexing starts with 0. Last index is basically the top, wherever your current size of the heap is at right now. So we keep track of these two to ensure that the last index would never exceed your max index. And the other global elements that we are going to keep track of is the instance of your comparator. So this is a Java interface, and we're trying to create a concrete class. So you can instantiate this with your own implementation of the abstract compare methods, right? That compare method gives -1, 0, or +1, right? Depends on the size of your the two objects that you're trying to compare. So this allows us to, if you're, let's say, do a reheap up, right? Let's say if you're inserting something into it. So this one is going to have to go up, right? Its way up to reheap, right? If that is the case, we have to compare the nodes, right? Against, so basically this node against this parent, and the parent against this parent, so on and so forth. So we need these comparators here. Okay, so without further ado, this is the structures that we have here. Let's start up with how we enqueue, right, elements. So this is the enqueue method, which is also available in your heap priority queue.java class. As you can see here, this one takes t elements, right? So this generic type data elements goes in there. So if last index is the max index, which means that this entire heap is basically over buffered, you want to throw an overflow, an exception. Otherwise, right, this thing we're trying to do is, let's say if this heap is at this locations right now, it's at this stage, right? And you're trying to enqueue this, right? This question mark, which is your elements, right, at this locations. We need to basically increment our last index plus, right, to accommodate for it. Because remember, everything is sitting inside this array. So you're keeping track of your last index. Your last index was here. You're adding a new one, this new element. So you have to create a new one. So this last index is going to be incremented, right? This will point you to the new location for insertion. So at that moment in time, right, you can do an array. So this elements, right? This is an array list dot add at that index and the elements that you're inserting into it. So this dot add is the method inside the array list as part of your Java util. And then the next thing up is to do a read heap up, right? Remember, when we enqueue something, right, we always add our element, right, at the end, right? This is the question mark at the end of your array list. Or at the basically at the locations where this incomplete tree is, the last elements inside this tree. And then we do a reheap up, because this one has to bubble its way up to balance out, right? To balance out or readjust this heap. So let's take a look at this reheap up algorithms, right? As the picture on the next slide. So let's move on to the next one. So this is the pictorial representation of what would happen, right, when you insert something into a queue, into your heap. The very next available, right, this is index whole, right, HOLE. So I guess the author uses the whole. At this location is where a new question mark, right, new element gets inserted in there. So once you have it inserted, what happens is you would have to basically compare that element against its immediate parent. There's only one, to make sure that this element stays at where it is, or this element is bigger, right, than its parents, then it's swapping, right? This moving up, which means swapping of the parents, right, which was G against this whole. So generically, whatever this whole is, this is the your element. Then continue its way up, right? Now you have to go against, right? Its parents again. And if this thing is bigger than or less than, right, it depends on the property. It either stays at where it came from, or it will swap with its parent. So so on and so forth. So if the whole that or the elements that you're trying to insert is this letter K, right? Then this K is going to be at here, right? So this is kind of a the causal effect here when depends on the element. So this is the reason why we have comparator in place, because when we are at any given locations, we have to compare basically its parents, right? In terms of their values and decide whether a swap is necessary. So that is comparator. And the other thing is keep in mind though, right? At any given index, we can find out its left child and also right child's indices, as well as at any given index element, its parents index. There was the three formula we were talking about. So let's just review these as we go into the next slides here. Okay, so before we cover the reheap up operation, let's just keep in mind, if you have, right, so this entire tree or heap is represented in this array list from up to down, right? So this is the tree, right? Something like this. And its representation is sitting in here, right? So there's stuff here, there's stuff here, there's stuff here. There's also indices, right? So let's just say if we have this element, let's just use the same notations that they have. So elements is the array list, right? Let's say if this element's at index. So this is a particular node that we have sitting inside of this tree, right? Somewhere. So I don't know where it is. So maybe it's this one. What is the index of this particular element, right? That's represented by element index in array indexing. So that array indexing parent relative to the index of that element is actually index minus 1 divided by 2, right? So we talked about this too. What about this particular element's child, left child and the right child indices? So left child index is index times 2, okay, plus 1. And right child, right, like we said, is index times 2 plus 2, okay? So we went over this, right, in our previous lecture. So if you don't remember these, make sure you go back to 4 or 5 slides ago in the video that came with it. So with that, we can pretty much navigate, right? Given an index associated with the elements, we can navigate to its parent because we know the parent's index. We can navigate to its left child because we know this formula, or its right child, right? So regardless whether there's child or not, maybe there's right, or maybe perhaps we're at the root level. It doesn't really matter. This formula apply, right? So the very first thing we need to do is when we do reheap up, remember the element is currently at last index. So what we want to do is to set up this hole. This hole is basically that index at where, right, wherever this new element is supposed to be at. Initially, this new element is at the whole area, which is the last index, okay? I don't particularly like the use of hole here, but if you go back to the previous slide, it shows, right, that void you're trying to get to. So there's a couple things that we need to be mindful of. There is a while loop. This while loop is the one that allows you to recursively go back up, right, from this location to this location and then this location, right, bubble yourself up. Sometimes people call these reheap up a bubble up operations. It doesn't really matter what you call it. So as long as, right, whole is greater than 0, remember if whole equals 0, right, in this, so what is the index 0? If you have an index 0, this is what we call root, okay? So this is basically saying that we're gonna have a while loop here that allows you to bubble up all the way up until right before you get to the root, not including root, right? Because whole is greater than 0. So that is the premise here, right? So if the while loop does not, right, keeps going, what you end up with is you're going to be at a positions where you're right before the root, or maybe several levels down before the root, because the other condition is NN, right? This is the NN conditions that you're trying to compare this element that you're inserting against its parent. So this parent in array list is elements dot get. Okay, this is the method that you have to use, and the index that you have to be using is the parent's index, right? This parent index is what we just talked about here, right? Given this whole, which is the index of the current elements right now, whole minus 1 divided by 2, right? This is the location of this particular element's parent. Now, if you do a compare, right? Remember, if this element is bigger than this parent, right? Then what do? Then what you want to do is just make sure that you can do a swap. Okay, so now actually in this case, yes, if the elements is bigger, then you have to bubble itself, because we're talking about max heap here. So element has to move up, right, from this location to this location, because the swapping has to happen. So the swapping actually happens when we do an element set at this whole. So at this whole location is what we the elements is being inserted at. Your parents is right here. So this parent is going to be set at whole. So basically what you're doing is the parent used to be here, right? And the whole is here. So the very first thing you need to do, right, as part of the bubble up, is to ensure that your P is right, your parent is right here. That's what this is, right? Set. And then your whole is at a parent. So basically, if you set P here, then this one is going to be empty, right? So P is going to be at this location, and H is going to be at this location. The whole is going to be at this locations. Okay. And then guess what? You just do it iteratively, right? This is the while loop. As long as the whole is greater than 0, and then you just do a comparisons again that this element is going to be at it's bigger than its parent, then it just could keep bubbling up. So maybe, and this bubbling up is going to be another parent, and then another parent, another parent, just keep going until, right, you get to the point where you're right before, you're basically at the root level, like whole equals 0, then you stop this while loop. Or at the moment when this entire compare gives you a equals 0, right? Equals 0, actually, in this case, equals 0 or less than 0, right? So these are the two conditions that will propel, right, this recursions, this iterative, right, methods to continue. Now, once this is over, you're basically done, right? And then what we need to do is to set the elements at that destination, that whole locations, okay? That whole locations. It is very possible that after the while loop at the whole, right, because you're doing whole equals whole minus 1, right? It's already at the root. So it is possible, right? If this whole is at the root level, then this element is going to be set at the root. Okay. If not, then it will be right before the root, or maybe 2 levels down the roots, maybe 3 levels down the roots. But this allows you to bubble up until, right, up until the compare produces either a equivalent 0 or less than 0. So what happens when a compare equals 0? That means that element has the same value as the parent. So when that happens, right, like we said before, the property heap stops, right, the bubble up, because if the elements are the same, you don't want to swap anything at all. So this is the reheap up, and this involves the iterative method. You can also turn this reheap up into a recursion as well. Sometimes you see people do that, but iteration is very easy to understand, and this wraps up the Enqueue method in terms of the implementation making use of an array list.